So for SN1 and SN2 substitution reactions, the best way to start is kind of look at what are the three possibilities. What I want to do is I want to take this hydroxide group, which has free electrons, and I want to kick out the chlorine on my chloromethane here. So I want this to replace this in a substitution reaction. And there are three different kind of methods for that to occur. The first one is this just leaves on its own first. So something in the solvent bumps into this and then it gets removed and it goes off with something else. Now at that point then, I have a trigonal planar, a flat carbocation, okay, which is not stable. So very quickly after that, this can come in, bond, and now I have my methanol. Okay. Alternatively, simultaneous, I can have this hydroxide come in from the other end, form a bond with this kicks out, and then the hydrogens will deform over to the other side, and I'll end up with a methanol like that. Now I can't actually bond that using the model kit, but essentially I would invert the chemical, and it would be a simultaneous reaction where the one bond is forming as the old bond is breaking. The third possibility is that at the hydroxide could come in first, form a bond, and then afterwards the chloride would leave. That actually, the carbon does not have the orbital capacity for that to occur. So SN1 and SN2 are the two mechanisms that we see for that. And what's interesting is that both occur, but on different levels for different reactions. So what we want to do today is kind of highlight what those two things are, but also go through when will we see one versus when will we see the other. Now, here are the three ways that we can do this. We can have a new bond forming as the old one breaks. That's SN2, which is because it involves two things at once. Okay? New bond forms, then the old one breaks. This one does not occur. And then the old bond breaks first, and then the new one forms, and that would be SN1 because essentially the old bond breaking dictates the reaction. And because that's occurring with just one chemical, that's attributed to one. Okay? So number 2 doesn't work at all. Number 1 and 3 will, and we want to go through and look at why each will occur at different points. Okay? So the biggest factor is whether a carbon is primary, secondary, or tertiary, which basically means how many things are attached to your carbon. So in a primary carbon, you have one carbon group attached, or one leaving group, I'm sorry, and then the rest would just be hydrogens. So I'm going to backtrack off of that. Primary carbon would look like this. It would be a leading group, and then some other carbon group attached. In a secondary carbon, this hydrogen would be another carbon group. In a tertiary carbon, all of these would be carbon groups, and then I would have my leading group. So the biggest factor to determine which one will occur is how many other carbons are attached to the carbon with the leading group. Now, the leading group is going to be something that kind of stands out. So something with an oxygen, something with a sulfur, something with a halogen, or just a halogen or whatever. That's going to be the thing that actually ends up leaving that gets something else replacing it in a substitution reaction. Okay? So if I have just a primary carbon with my leaving group attached, then that's going to mean that we're probably going to see SN2 occur. Barring extreme circumstance, two things cause this to be the primary mechanism for this. One is that there's a lot of space. Hydrogens are tiny. And so for a nucleophile to come in here and hit this carbon is actually pretty easy. Whereas if I have a bunch of bulky things attached, it's not so simple. Okay? The second thing is, in order for the SN1 reaction to occur, it has to form a carbocation. And so it's just more difficult with this. And there's not a lot of electron density around this, and so it's very, very unlikely. Okay? So the actual mechanism here for an SN1 reaction on the other side, we have a leading group here that actually leaves, taking its electrons with it. We form this carbocation intermediate, a trigonal planar thing with a positive charge on the carbon. Very unstable. Okay? And then after that, a nucleophile can come in from either side and form our new molecule. Okay? Now, SN1 reactions will occur when you have a tertiary carbon. So if you have a carbon bonded to a carbon, bonded to a carbon, bonded to a carbon, and then a leaving group present, then you're going to see SN1 occur pretty much every single time. Okay? Now in non-IB land, there are also elimination reactions that will occur for this. But we're going to keep and just look at the substitution elements of this. Okay? So for tertiary carbons, this is the mechanism you would see occur. You would see the leaving group leave, taking these electrons with it. I would have a positively charged trigonal planar carbocation. And then after that, my nucleophile would come in and bond to this. So for tertiary carbons, we'll see SN1. For primary carbons, we'll see SN2. So the fun one is, well, what happens if you have a secondary carbon? And the answer is either or. It depends on some other factors. Okay? So SN1, we're going to see this going on whenever we have tertiary. And then SN2, we're going to see when we have primary. When we have a secondary carbon, that means that either could happen, and so now we need to look at what else will influence this. Okay? So this is our biggest thing. Now, you do need to be able to recognize if something's primary, secondary, or tertiary. Here, we have a carbon. There's one carbon attached, so this would be primary. Okay? Here's our leaving group here. I have a carbon here, so this would be secondary. This one, on leaving group, is a hydroxide. I have 1, 2, 3 carbons attached. This would be tertiary. And then here, I have 1, 2, 3 carbons attached. So this would also be tertiary. So in the last two, the 3 and 4, we're going to see a primarily SN1 reaction occur. Okay, and the first one up here, this is going to be SN2. But then the question is, well, what happens for this? This could be either or. And so now we need to kind of look at some more details to figure out which one of those will occur. Okay. Solvent is one of the factors. What the leaving group is one of the factors. And even temperature can influence this. So we want to look at why each of those things will have certain effects. So solvent is important because solvent's going to interact with your chemical. And if you need to remove something to do an SN1 mechanism, you need to have a solvent that will interact well with it. Additionally, solvents can interfere with the nucleophile in an SN2 reaction. So there are 3 types of solids. There's polar aprotic, which A means not. So we're looking at something without basically a hydrogen that can be acidic. Okay. So there's dimethyl sulfoxide, tetrahydrofuran, methylene chloride, acetone. These are all solvents that don't really have hydrogen bonding, that don't have an acidic hydrogen on them, but are polar themselves. Polar protic are things with hydrogen bonding capabilities. So water, ammonia, alcohols, acetic acid. So a lot of these are capable of being acids. And additionally, they're very, very strong at interacting with the chemicals. And then we have nonpolar solvents. Okay, so nonpolar solvents, just things that aren't polar. Alkanes, benzene, toluene, cycloalkanes, ethers are a little polar, but non-polar enough that we could put them into this group. So which solvent you carry out the reaction in will influence whether you get SN1 or SN2. Now there are 2 kind of key factors for this. Okay, one is that when we're looking at SN2 reactions, these are going to be fastest in non-polar solvents because a polar solvent will interact with the nucleophile. And it will reduce its ability to go in and collide with that and kick out the leaving group. And so if I have a really good solvent, and here's my nucleophile, and I'm coming into a secondary carbon with the leaving group, the solvent being around this is going to reduce these electrons' ability to go ahead and kick out this leaving group. The whole point of a nucleophile is it has a source of electron, a source of negative charge. And so if I have this stabilized with a bunch of water molecules, then the electrostatic interactions with this now change, and that will reduce the ability of this to work. So what I want here is I want something that's nonpolar. And if I can't have nonpolar, aprotic acids will be better than protic, because if I have hydrogen bonding, that's going to cause an interaction with here that's going to reduce the electrostatic impact on this. So for SN2 to be favored, I want a nonpolar solvent, or I want a polar aprotic. Okay? And that's based on the interactions with the nucleophile itself. Now if I go ahead for SN1, now the key thing is I need to be able to pull that thing off of the carbon to form the carbocation. So now I want a solvent that's really good at interacting with a carbocation, stabilizing that very unstable product. So now I do want something polar, and I want something that's protic, meaning that it has hydrogen bonding capabilities. So this is more based on interacting with the carbocation. So if I have a secondary carbon with a leaving group attached, if I use a polar protic solvent, that's going to lead towards the carbocation formation, and I'm going to see SN1. If I have a non-polar solvent, that's going to lead towards SN2, working a little better. Okay. Second thing that's going to influence which one you get is the nucleophile. So what's coming in and interacting with this? If you have a really strong nucleophile, that's going to participate in the reaction. If you don't, it's going to take until that carbocation forms till you can get to the point where you can come in and interact with it. And so the strength of the nucleophile, which basically means how much negative charge can I interact with this. So things that have a lot of negative charge concentrated in a small space are really good at being nucleophiles. Now when we get solvents interacted, that actually can switch up a little bit. So when I have solvents interacting, one of the key things that's really good for a nucleophile is how polarizable the thing is. And so sometimes in solvents, the larger ions end up working even better. So there are multiple things that we can see for trends for nucleophiles. Okay, the more charge, the better. So hydroxide versus water. Hydroxide is going to be the better nucleophile because it has that negative charge, and basically it doesn't have the H+ for repulsion. And so when that comes in and comes towards the leaving group and the carbon with the leaving group, that's going to be better at pushing those electrons out. This is not going to work as well. If I have an amide or ammonia ion, then this is going to be a better nucleophile than ammonia, methoxide versus methanol. So one of the things you can do is if you have a weak nucleophile like water or ammonia or methanol, you can add base to it, and that will help facilitate the reaction to occur, where the base can act as a good catalyst. Okay, so having negative charge versus not, the negative charge would be the stronger nucleophile. Okay. As electronegativity goes down, the nucleophile becomes stronger. Okay. So here we're looking at nitrogen versus oxygen versus fluoride. This is the better nucleophile because it's able to give electron density to the other thing. This is very electronegative, so it has a lot of protons, a lot of effective nuclear charge, and so therefore the electrons on this are closer. This has had more proton repulsion, and it's not able to interact with the carbon as well, and so it doesn't work as well. Okay. If the thing is big, that's actually going to just interfere with the reaction. So if I have something that's got like a secondary or a tertiary attached to it, this is not going to be a very good nucleophile. So if I'm looking at methoxide versus 2-methyl propoxide, this is not going to be a very good nucleophile. This just literally can't interact with the chemical without getting caught in other things and getting bumped into stuff. This one is the one you'll probably see the most, and this is with solvents under consideration. But if we're comparing things that have various size, the polarizability in a solvent is pretty critical. So iodide is going to be better than bromide, than chloride, than fluoride. Now if you do it in the gas phase, that trend will actually reverse. We're going to be looking not in that sense. We're going to be looking in solvent. And so the larger it is, the better this thing is going to be able to contribute electron density by being able to shift its electrons around. And so this will make your best nucleophile, and therefore that's going to encourage an SN2 to occur over an SN1. So essentially our question is, at the end of the day, is it SN1 or SN2? So here's an example. So here's our carbon, here's our leaving group. Okay, it's the weird thing that stands out. I have 2 carbons attached, so this is secondary. So it could be either or. So now I want to look at what's my nucleophile. Well, cyanide is a pretty strong nucleophile. That's indicative of SN2. And then acetone is a polar aprotic, so it's not going to interfere too much with the cyanide's capability of kicking that out. And so we're going to see SN2. And so that's the reaction mechanism that we're going to see the most. Now down here we have a weak nucleophile. Okay, and that's also kind of our solvent in this case. It's a polar protic solvent, and so therefore this is going to favor SN1. So we're going to form the carbocation first. This is going to leave. Then later the methanol is going to attach and then have the H+ removed to form our different compounds, to form our product. Okay? So what your nucleophile is, what your solvent is, and then most important is this primary, secondary, tertiary. All of those things will have an influence on whether it's SN1 or SN2, and that's how you want to approach that and come through and look at which of those things it's going to be.